In this class of APL 100 Engineering Mechanics, we are going to prove a very useful vector relationship. That vector relationship is written at the very top of this slide. Here. This relationship is about a vector A shown here, which is being observed simultaneously by two different observers or two different reference frames. One is the reference frame F and the other is the reference frame M. The observers who are tied to these reference frame are simultaneously observing this vector, same vector A. And they report that the vector is changing. In general, the vector is changing. Our friend who is tied to frame F reports that change as what I have shown here. Symbolically, rate of change of vector A as observed by the observer tied to frame F. Whereas our friend who is tied to frame M reports this much change in the vector M, vector A. It turns out, in general, these two reported changes in the same vector with respect to two different frames will be different. And the difference is actually this much, which is the cross product of the angular velocity of frame M with respect to F and that vector itself. Very useful relationship. Very useful relationship. We are going to prove this relationship. And once we have proved that, we will be in a very legitimate position to use it while solving different kinds of problems. Let's start the proof. So in this frame M, I have identified a point O prime and three mutually perpendicular unit vectors. And all these four items are fixed to frame M, are M fixed. As I said earlier, A is an arbitrary vector. Omega mf is the angular velocity of M with respect to F. Now I am going to write A using these three unit vectors which are fixed in frame M. You can say that I am trying to express A using M fixed Cartesian coordinate system O prime this coordinate system. This is the expression of A written here, where A1, A2 and A3 are the scalar components of vector A in this coordinate system. And these scalar components may be time dependent. There is no restriction on that. I am going to hit this equation, the expression of A, with this operator, which is rate of change of A with respect to M. What do I get? I get what I have on the right hand side, and then I apply product rule of differentiation and I go ahead and differentiate each of the three terms. For example, this term, when we take the derivative, will give you two terms. which are written here. Since A1 is a scalar, there is no need to put the baggage, whether it is with respect to f or m, doesn't matter. But when the derivative is of a vector, you must specify the rate of change is with respect to which reference frame. In this case, it is m. Similarly, I go ahead and split A2 I split A2 E2 into two terms here and here, and similarly I split A3 E3 into two terms which are written here. But then we remind ourselves that this E1, E2 and E3 are fixed in M, which implies that the rate of change of E1, E2 and E3 with respect to M will individually be 0. Perhaps this part is not visible. It shows dE1 dt with respect to M. Just like this expression here, we have rate of change of E1 vector with respect to M. All these should be individually 0, which means that this will go away, this will go away, and this will go away. We are left with three non-zero terms, which are these. Okay. We move to the next slide with this simplified expression. We move to the next simplified form. Since these terms have been removed, since I have removed these terms, I am left with this expression. Here I have also used the shorthand that dA1 dt is I am simply writing that as A1 dot, and then dA2 dt as A2 dot, and dA3 dt as A3 dot. I call this equation as 1. But then I remind myself that A is A1 E1, A2 E2, A3 E3. If I now take the derivative of f, derivative of A with respect to f, I will get the expression that I have here. So this one I am keeping in reserve. I am re-expressing A in terms of the Cartesian, frame fixed Cartesian coordinate system of M, or M fixed Cartesian coordinate system, and I write dA dt f as this, which has 6 terms. But then we realize that the first 3 terms which are written here, they are nothing but rate of change of A with respect to M. That's what I have brought here, the blue color. And the remaining 3 terms, this one, and this one, will come here. So my expression, the current expression is rate of change of A. My current expression is the rate of change of A with respect to F is rate of change of A with respect to M, and 3 individual terms, this, and this. Since small e1 is fixed in frame M, If I want to find the rate of change of E1 with respect to F, I can write that in terms of the angular velocity of M with respect to F. We have derived this in the last class. Similarly, the rate of change of E2 with respect to F can be written in terms of the angular velocity of M with respect to F and E2, and the rate of change of E3 can be written in this manner. I call this set of equation as number 4, and if you take number 4 and put this back in 3, you get rate of change of A with respect to F equals rate of change of A with respect to M, and then these three individual terms, which can be combined in this manner. I take omega mf cross outside and take A1 E1, A2 E2 and A3 E3 inside. That leads us to this form of the equation. Now here, this bunch of terms that we have grouped together, that is simply the full vector A. Thus, we are now in a position to reach the conclusion of this derivation that rate of change of A with respect to F is equal to rate of change of A with respect to M plus an additional term, which is the cross product of the angular velocity of M with respect to F with the vector A itself. We have been able to prove this statement. We will use it very soon to solve problems and also to make further derivations, further useful derivations. Mind you, this equation, what we have arrived at, this boxed equation, is a vector equation. You will realize that to derive this, I used a frame fixed Cartesian coordinate system. I did use a frame fixed Cartesian coordinate system. However, the final form of the equation which I have expressed now, this is in full vector form, which is independent of coordinate system. Independent of coordinate system. In other words, I am saying that even if your working coordinate system is not frame fixed Cartesian coordinate system, it is cylindrical polar or path coordinate system, still this equation is valid. It's like this. You look at this simple equation F equals ma, which is the vector equation for the vector equation, the Newton's second law, vector expressed as a vector equation. We know that we can express the left hand side and right hand side in any coordinate system of our choice. The equation itself doesn't depend on the choice of coordinate system. That is what has happened here. I repeat, even though we have used a frame fixed Cartesian coordinate system to prove this relationship, the relationship itself is coordinate system independent. Moving on, now we want to introduce a new vector. That vector is the angular acceleration of frame M with respect to frame F. Frame M with respect to frame F. Angular acceleration is defined as simply the derivative of the angular velocity with respect to frame F. Symbolically, we will use this notation omega dot mf, and the SI units would be radians per second square. Note that the rate of change of omega mf with respect to f is the same as the rate of change of omega mf with respect to m. This is an interesting observation, and it follows directly from the relationship that we derived earlier the relationship that we derived earlier this relationship. Now this relationship is true for any vector A. Now if I set A as the angular velocity itself, I get the equation I have written here, that the rate of change of angular velocity with respect to f is equal to rate of change of angular velocity with respect to m, and then we come across the third term wherein we get omega mf being crossed with omega mf itself. That gives zero contribution, leading to this conclusion that the rate of change of angular velocity of m with respect to f is the same as the rate of change of that angular velocity with respect to frame m. In fact, such an interesting observation arises not only for omega mf. It turns out that any vector which is parallel to omega mf, any vector A which is parallel to omega mf, will lead to zero contribution arising from this term. And for such vectors, rate of change or the two frames with respect to the two frames will remain the same. Okay, this is a side observation we make in context of the rate of change of vectors. Moving on, our next topic is composition of reference frames. Composition of reference frames. So we have a composition or a combination or a collection of reference frame in context. I have shown them here. As RB1, RB2 and RB3. In context of these three RBs, these three reference frames or these three rigid bodies, there are two useful relationships that we want to derive. But before I derive those relationships, let's introduce ourselves, or let's remind ourselves rather of the symbolic notations for the different angular velocities that exist in the context of these three RBs. We can talk about omega 31, which will mean the angular velocity of RB3 with respect to RB1. You can talk about omega 32, which will be the angular velocity of RB3 with respect to RB2. And then you can always also talk about omega 21, which is the angular velocity of RB2 with respect to RB1. Now, in general, we are dealing with a situation where these three angular velocities are different from each other. In this context, we wish to prove these two relationships. These two relationships. One and two. The first relationship is about the three angular velocities in context. It turns out that the three angular velocities, 3 with respect to 1, 3 with respect to 2 and 2 with respect to 1 are not independent after all. They are related to each other, and that relationship is given in this equation. So 3 with respect to 1 you can write as 3 with respect to 2 and then 2 with respect to 1. It is as if I am taking an intermediate step to find omega 3,1. If my interest is to find omega 3,1, this relationship is telling me that you can take a path in which you first find omega of 3 with respect to 2 and then you find omega of 2 with respect to 1 and you add them together. That gives you omega 3,1. The second relationship is about angular velocities. The second relationship is telling me that the angular velocity of omega, angular velocity of 3 with respect to 1, again can be found in steps such that first you find omega dot 3 with respect to 2 and then you find angular acceleration of 2 with respect to 1. But that is not all. It seems intuitive that if you want to get angular accelerations from the first relationship here, you just put dot, dot and dot on all the three terms and you will be fine. However, this is not correct. There is an extra term that appears, a cross product between the angular velocity 2 with respect to 1 and angular velocity of 3 with respect to 2. We will prove it mathematically. There is no direct or simple physical way to explain it, at least to the best of my knowledge. But then the consolation is that we can prove this non-intuitive relationship using mathematics precisely. That's what we are going to do next. Let's start with the proof of the first relationship, which relates omega angular velocity of 3 with respect to 1. It calculates that quantity in two steps, to omega of 3 with respect to 2 and then 2 with respect to 1. Let's prove this. To prove it, again we recall this relationship. The rate of change of a vector observed from f and then the same vector being observed with respect to m, the way they are related, it's here. Symbolically, you can also write, we will write, following our own notation, we can write this expression simply as a dot f and we can write this as a dot m. Just to save some space on the slide and to save some time, you can use this alternative notation as well. Now, starting with this expression, I am first going to put f as 1 in this and m as 3. That gives me this equation. Putting f equals 1 and m equals 3 gives me this equation. I call this equation as 1. Then I go back to this equation and I put f equals 1 and m equals 2. I am allowed to do that. I am allowed to choose m to be any intermediate reference frame. That gives me another expression for a dot with respect to 1 and that expression is written as equation number 2. Now since the left hand sides of 1 and 2 are the same, I am going to equate them and that leads me to the equation I have here. which is the rate of change of A with respect to 3, and then cross product of omega 3 1 and A, and on the right hand side I have rate of change of A with respect to 2 and the cross product of angular velocity of 2 with respect to 1 and A itself. Further, I am going to write what is appearing on the I'm going to write I'm going to rewrite rate of change of A with respect to 2 now using 3 as my intermediate frame, and this expression becomes what I have here. A with respect to 2 being written as A respect to 3 plus omega 3 with respect to 2 crossed with A, and then on the other term just stays the way it is. Once I do that, I realize that on both sides of this equation I have A dot 3, A dot with respect to 3 appearing, which I am going to cancel out readily and take all the terms on the left hand side, making this equation appear as what I have here. Then I take A as a common factor and a group of terms involving only omegas, various omegas, appear on the left hand side. Now recall that my choice of A is arbitrary. This equation must hold good for every A that you can think about. And if that is the case, then for this equation to be valid, we are left only with one choice, but to conclude that this factor itself should be 0, which when rearranged gives me the relationship between the angular velocity of 3 with respect to 1 in terms of 3 with respect to 2 and angular velocity of 2 with respect to 1. That completes my proof for the relationship that exists between the angular velocity of the 3 bodies in context. Now let's take an attempt at proving this equation, which is the angular acceleration of 3 with respect to 1, how it can be written in terms of the angular acceleration of 3 with respect to 2, and angular acceleration of 2 with respect to 1, and the cross product between the angular velocities of 2 with respect to 1 and that of 3 with respect to 2. Let's prove this relationship. The proof of this relationship starts with the definition of omega dot 31, which is written here, and then I am going to substitute omega 31 in terms of 32 and 21. This relationship is the same which I proved on the previous slide. When I put these things in here, this is the expression I get. Now if I go ahead and differentiate what is inside the parenthesis here, I get two expressions, 3,2 with respect to 1 and 2,1 with respect to 1. Now as far as the second term is concerned, this is precisely what I would use the notation omega dot 21 to represent. This is the angular acceleration of 2 with respect to 1. Whereas the first term is currently in this form and it needs some more simplification or processing before I can prove my original statement, which is here. Now again, I recall that for any vector q, I can write this expression. Any vector q, I can write this expression, rate of change of q with respect to 1 equals rate of change of q with respect to 2 and then omega 2 1 cross q. I am going to set q as omega 3 2. Once you put omega 3 2 as q, once you replace q by omega 3 2, this equation becomes what I have here. And you would see that there is this cross product between two angular velocities appearing there, which we do need in our final expression, which requires the proof. Okay. So I am going to go back to the expression that I derived earlier, omega dot 31. This is the step which was up there just a little while ago. I called that as equation number 1. I am going to replace this with what I have in the previous expression, and that gives rise to this equation what I have. Now the term which is here, this is precisely omega dot 32. There is no ambiguity in this, omega dot 32. So I bring back this notation and I arrive at this final form, which is precisely what my intention was, which was my intended relationship earlier. So angular velocity, angular acceleration of 3 with respect to 1, 3 with respect to 2, 2 with respect to 1 and 2 1, and then 3 2 angular velocity. So we have proved this relationship as well.